Hi, Hazel. What to do? Hi, Hazel. What you do? What you do? Hmm? What you do? That not for you. Hello, class. If you're here, I'm gonna wait until the number of viewers reaches 15 or so, and then I'll get started. What you do, Hazel? I'll put this up here. Over here. There you go. There you go. Hello. Good morning. Waiting for 15 people before I get started. Hola, ¿cómo estás? All right. One more person. There we go. 15 people. Excellent. All right. Couple announcements to get started. First of all, yo también. I don't know what that means. Does that mean? I don't know what that means. Did I tell you guys I'm taking Spanish 1 with Maestra Viera? It's second period, so tomorrow morning at 8, I will log into her Zoom classroom and I will participate. Because I want to learn Spanish. And I was like, why not? Just take it from another teacher. Me too. Okay. So, today, first thing I want to remind you to do is submit the daily attendance. Okay? So if you haven't done that already, please do that at this time. The second thing I want to remind you is that the first quiz that I assigned you last week is due tomorrow at 11:59 p.m. Okay? So the way that the quizzes work is any quiz I assign this week will be due the following week on Friday. So you have at least a week to do the quiz. Okay? That is not a way I would like to learn Spanish. That does not sound very pleasant. All right. So what are we going to talk about today? Well, today we're going to connect vectors to physics. Okay? But first, what I'm going to do is I'm going to do a little calculus review because every year when I teach this class, there are maybe 2, 3, 4 people who are taking calculus for the first time while they are enrolled in my class. And so I'm going to teach you just one really basic thing from calculus so that you can understand today's lesson. Okay, it's really simple. So I'm going to teach you how to take the derivative of a power of t. Okay, so what if I have something like 3t to the 5th power? Okay, and I want to take the derivative of that. So this means take the derivative with respect to time. And so what you want to do if you take the derivative with respect to time, so d dt, you bring the power down, and so you're going to ignore this factor of 3 in front, okay? And you're going to bring the power down and multiply it by the whole expression. So we have 5 times 3, okay? And then we're going to take the power of t, and we are going to reduce it by 1, okay? And then we can simplify it. So 15 t to the 4th. That's how you take the derivative of a simple function like this, a power of t, okay? Now, I'm distracted because Hazel is staring at me. What do you want, Hazel? What do you want? All right, so there are a couple of cases of this that can be might confuse some of you. So in particular, what if I wanted to do what is the derivative of a constant, like 7? We could think about 7 as t to the 0 power, right? Because anything to the 0 power is 1. So 7 is equal to 7 times t to the 0 power. And then we just apply the same rule, okay? We bring the factor out in front, and we just get 0 times 7t to the minus 1, okay? Which is just 0. So the rule of thumb is that the derivative of any constant, like the derivative of minus 3, for example, is 0, all right? Another derivative that can sometimes be confusing, well, it's not confusing, but, I'm going to go over it, is what if we have the derivative of, for example, minus 4t, like that. You want to think about t. If we don't explicitly put the power in, then the power of t is 1, right? So we're going to multiply by 1. So we have 1 times negative 4. And then I reduce the power of t by 1, so I get t to the 0 power. And t to the 0 is just 1, so the factor of t actually goes away. We just get minus 4. Okay? So those are some examples of derivatives. What if you have a sum of two terms like this? What if we had 2t to the 6th minus 7t squared, and we want to take the derivative of that? Well, this is the sum of two terms, so we take the derivative of the first part, we take the derivative of the second part, and we combine them. We just add them together, okay? So taking the derivative of the first part will give me 6 times 2 times t to the 5th. Taking the derivative of the second part would be 2 times negative 7 times t to the 1 power, which is just t. And then we simplify. So we get 12t to the 5th minus 14t. All right? So that is the calculus that you are going to have to know for today's lesson. All right. So how are we going to connect vectors to physics? There are many vectors that are useful in physics. Okay. The first vector is called the position vector, which is denoted by r of t. Okay. Hang on, I want to check my desktop first. All right. So what I want to imagine is I have a particle that is moving around like this. Here's the path of the particle. Here's where the particle is at time equals 0. Here's where the particle is at time equals 1 second. Here's where the particle is at time equals 2 seconds. So, And then we have an origin of our coordinate system. So maybe there's an origin that is right here. There's the origin. The position vector extends from the origin to the location of the particle. So this would be r of 0, position vector of 0. This would be position vector of 1 second, at 1 second. This would be position vector at 2 seconds, and so on. Okay? Now the position vector, if we look at it, well, the x-coordinate of the particle is how far over it is, and the y-coordinate is how far up it is. So the position vector is just x of t times I hat plus y of t times j hat. My former student Chris asked, where's the donation button? I know the students don't have any money. So I'm doing this for, you don't have to pay me. You know, it's kind of interesting in distance learning. I was thinking about it, and distance learning kind of takes a lot of stuff out of the equation, right? Like, what is the meaning? What is the usefulness of administrators if we're all just working from home doing distance learning? Like, why do I even need the school anymore? Why don't I just go off on my own and teach my own lessons and charge kids for it? I've thought about it. Okay, so I'm going to ask you guys, what does this mean? If you know the answer to what that means, go ahead and type it into the live chat, okay? And while I'm waiting for an answer, I'm going to go ahead and talk about the velocity vector. So the velocity vector is v of t, and it's equal to the derivative of the position vector. So yeah, it is the magnitude of the position vector, but what does the magnitude of the position vector mean? Okay, what does magnitude of a vector mean, and what would that mean applied to position? Okay, so anyways, the velocity vector, we're going to take the derivative of the position. All right, so yeah, we've got a response that says distance. So the magnitude of the position vector would be distance from the origin. Okay? Distance from the origin. Okay? It would be the length of that vector. Similarly, if we did what is the magnitude of r of t minus some random vector a, that would be the distance from A. All right. So that's position vector. With velocity vector, we're taking the derivative of the position vector, okay? And how do you take the derivative of a vector? Well, you take the derivative of the first component, and then you take the derivative of the second component, and you add them together, okay? So it's just dx dt times I hat plus dy dt times j hat. Okay? So sometimes this is rewritten as v sub x times I hat plus v sub y times j hat. And this is referred to as the x component of the velocity, and this is referred to as the y component of velocity. Okay? So what is the velocity vector? Well, the velocity vector is essentially speed with direction. So if we do the magnitude of the velocity vector, that is equal to your speed. How fast are you going? Okay. The direction of the velocity vector is equal to the direction of travel. Okay. So going back to this picture that I drew here, the velocity vector is going to point tangent to the path. So the velocity vector here points tangent to the path. The velocity vector here points tangent to the path. The velocity vector here points tangent to the path. Now I'm drawing this arrow to be longer to indicate a higher speed. Why do I say it had a higher speed? Well, if we look at between 0 and 1 second, it only went from here to here. But from 1 to 2 second, it went all the way over to here. That's a farther distance of traveling. So the longer the arrow is, the higher the speed. And wherever that arrow points is the direction of travel. Okay? I need to darken the path. It's just going to be a messy diagram. You can ask me about it during the second portion of the class if you have more questions. And then we have the acceleration vector, which is denoted by A, and it is simply the derivative of the velocity vector. Okay? Now, one of the things that's important, and this is especially going to be important if you are taking physics for the first time this year, as some of the people in this class are, is we need to know what are the units of these quantities. Any physics quantity has units associated with it. And to indicate units, I will put square brackets around the quantity. So units of position vector are meters. We're using the metric system, okay? Units of velocity vector are meters per second. Units of acceleration vector are meters per second squared. Okay? All right. So let's apply all of this. Let's do... Oh, and one thing I wanted to say is that all these definitions... Better box these definitions in. These definitions apply in any number of dimensions. So they apply in 3 dimensions. They apply in 4 dimensions, like you might encounter in special relativity. So the definition is exactly the same, no matter the number of dimensions. Okay, so let's do an example. What if I have a position vector that is equal to negative t to the third times I hat plus 2 t to the fourth times j hat. And I'll put parentheses m to indicate that whatever answer I get is going to be measured in meters. So we're going to ask some questions about this, but first of all, let's get the velocity vector. So to get the velocity vector, I want to take the derivative of the position vector. Okay. So taking the derivative of that, of the first term, I bring down the 3, and I reduce the power by 1. So I get minus 3t squared. And then taking the derivative of the second part, I bring the power down, giving me 4 times 2 is 8. And then reducing the power by 1, t cubed, j hat. And then I'll put parentheses meters per second to indicate the units. to get the acceleration, we take the derivative of this one. So again, taking the derivative again, we bring the power down. So we multiply -3 by 2 to get -6, reduce the power by 1. Do the same thing with the j component. Bring the power down, so we get 3 times 8 is 24. Reduce the power by 1. And then we put the units in parentheses afterwards. Excellent. So now let's ask some questions about this. First of all, how far from the origin? At time equals 1 second. So first thing I will do is I will plug in t equals 1 for the position, okay? So r of 1 is equal to, plugging in 1 for time, I get -I plus 2j. And then to get how far from the origin, I want the magnitude of the position vector. So to do the magnitude, we do the Pythagorean theorem on this vector. So I get square root of -1 squared plus 2 squared, which would be square root of 5 meters, which you would then convert to a decimal. Okay. What if I asked how fast is it going at t equals, let's say, 2 seconds? Now these numbers can get large because we're taking powers of number, so it could be a big number. So the velocity at 2 seconds is going to be, plugging in 2, we're going to get 4 times 3, -12 I hat. And then we're going to have 2 to the third, which is 8 times 8, plus 64 j hat. So that's the velocity vector at 2 seconds. And then to get the speed, which is how fast it's going, we're going to do the magnitude of the velocity vector at 2 seconds. So that would be the square root of -12 quantity squared plus 64 quantity squared. Now, I'm going to do some approximating here. 64 squared is much, much larger than 12 squared. So I could approximate the sum of these two as just, now I wouldn't do this if I was doing your daily quiz because you have to get really close to the exact answer. But if I was just ballparking it, I would say the -12 is negligible. So I get square root of 64 squared, which is equal to 64 meters per second. Okay? So if I were to actually do this with a calculator, square root of 144 plus 64 squared, you can see that the correct answer is 65. So I was pretty close to the correct answer, but I was yeah. So actually I was probably within 2%, but just to be safe, you would probably want to do the exact answer on the quiz. All right. So then there's another question I could ask, which is what is the direction of travel at t equals 2 seconds? The direction of travel, remember, the direction that the velocity vector points is the direction of travel. So I need to look at the velocity vector at 2 seconds. Okay, and I can see it's minus 12i plus 64j. Minus 12i plus 64j. So what does that vector look like? Well, it goes over to the left 12, and it goes up 64, which is 64 is like over 5 times as large. So maybe something like this. So that's 12. This distance is 12, and that's 64. And the vector goes like that. So the direction of travel is basically almost vertically upward, but a little bit to the left. Okay? I could ask you a question about acceleration, but I can just sense. I can sense it that you guys understand it, and that it would be not a good use of my time to do the acceleration vector. So I will move on. Okay. That was fun. I'm going to start throwing papers after I go to the next page. So now we're going to CHL, September 10th, period 7, part 2. Part 2. Or dose. Okay. So what are we going to do if we are talking about one-dimensional motion? If you have two-dimensional motion, then I's and J's are essential, okay? You know, R of t equals x of t I hat plus y of t j hat, okay? But if it's one-dimensional motion, we're basically not using this term. So we only have x of t I hat. And if we're not using an I and a j, then what's the point of even having the I to begin with? So in one-dimensional motion, we pretty much just describe the position as x of t, the position at time t, okay? And so what I'm going to do for the remainder of my time is we're going to derive 3 equations. They're called the Kinematics Equations, okay? And we used them a ton last year, all right? So we're gonna derive them this year using calculus. If you're just learning calculus for the first time, you don't have to watch this. You can simply begin working on the quiz for today, and go ahead and just wait for me in the Zoom room. But if you have already taken calculus and you're in Calc BC currently, or you took Calc AB last year, then go ahead and watch this, and we are going to derive the kinematics equations, which I think is neat. All right, so the basis for the kinematics equations is that the acceleration is equal to a constant. You cannot use the kinematics equations unless the acceleration is a constant. Okay? So what that means, because the acceleration is the derivative of the velocity with respect to time, we have the derivative of the velocity with respect to time is equal to a, which is a constant. Okay? In the previous example that I did, this would be an example of an acceleration that is not constant, because the formula for acceleration has time in it still. Okay? But this is a constant acceleration. So what I'm going to do is I'm going to go ahead and integrate both sides with respect to time. Okay? And I'm going to integrate from time 0 to the final time, which I'll also call t. Okay? Now notice how on the left-hand side the dt's cancel out, because I have t in the numerator and in the denominator. So this is just the integral of dv from, and the velocity corresponding to time 0, we would call that v naught, the initial velocity. And then the final velocity I'm just going to call v. Okay. Now, because the acceleration is constant, I can pull it out of the integral, and I just get this. Okay. Now, if you do the integral of dx from 1 to 3, the answer is just going to be 3 minus 1. Right? So this is completely analogous. So the integral of dt from 0 to t is just t minus 0, which is just t. So we get at on the right-hand side, and this integral is going to be v minus v naught. So if I add this over to the other side, I get v equals v initial plus at. So that's one of the kinematics equations. All right? So that's kind of neat, I think. I like that. Now let's go one step further. The velocity is the derivative of the position. Are you okay, Hazel? Hazel's panting a lot. Yeah, you okay? She's under the desk. I'm petting her. So we have the derivative of position is the velocity, which in the case of the constant acceleration is equal to v naught plus at. So we have this is true. Then what I'm going to do is I'm going to integrate both sides with respect to time again. I'm going to integrate from 0 to t. And the dt's cancel on the left-hand side, and I get the integral from the initial position to the final position. Okay? So on the left-hand side, my integral becomes x minus x initial. And on the right-hand side, I have two terms to integrate, v naught being a constant. So when I integrate that first term, I get v naught t. And when I integrate the second term, I'm integrating t, so it's 1/2 t squared. So I get plus 1/2 a t squared. So rearranging this gives me the main kinematics equation, x equals x naught plus v naught t plus 1/2 a t squared. So that's a really useful equation. Then there is a third kinematics equation, which I will put on the other page. And that equation starts from v squared minus v initial squared. So this one doesn't use calculus, it just uses algebra. I'm going to write v squared minus v initial squared as being equal to v plus v naught times v minus v naught. All right? If you FOIL that out, you can see that it's the same expression. Now, what is v minus v naught equal to? Well, if I look at this equation right here, v minus v naught is equal to at. So this term is at. And then plus v naught, well, if I take this equation and I add v naught to both sides, I get v plus v naught. I'm going to add another v naught onto the right-hand side, so it's going to be 2v naught plus at. Like that. Then I'm going to distribute the at. So I get 2v naught at plus a squared t squared. I'm going to factor out an a. And then I'm going to factor out a 2. Hazel, do you want a treat? Here you go. Hazel got a treat. Then I'm going to factor out a 2 as well. So factoring out a 2 from the first term would give v naught t. And factoring out a 2 from the second term, well, it doesn't have a 2, so it's going to leave behind a 1/2. Okay? So you can see that I have v naught t plus 1/2 at squared. And v naught t plus 1/2 at squared is just the displacement. So I have 2a delta x. And then I add the v naught to the other side, and I get v squared equals v naught squared plus 2a delta x. So, what have we done here? We have used calculus to derive the 3 kinematics equations. All right? Why did I just do that? You don't need to know that for the AP exam or for the IB exam. I just did it because I think it's neat. Okay? And but we are going to use these equations in Monday's lesson. Monday's lesson is going to be about solving difficult kinematics equation problems. Okay? So that is my lesson for today. And so I will see you in the Zoom room in about 1 minute. Catch you later.